Hi AP Stat, welcome to the first boot camp free response video. Let's get to work on some free response problems you'll need to be familiar with for your first boot camp quiz and for the AP test. So, problem number 1. The manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of the checkout line, data were collected on the number of customers in line who were in front of the selected customer and the time, in seconds, until the selected customer was finished with the checkout. The data are shown in the following scatter plot along with the corresponding least squares regression line and computer output. So we are asked 3 questions. Question number 1. Identify and interpret in context the estimate of the intercept for the least squares regression line. Now, I would not look at the graph up here. I would look at the computer output for this one, see if you can find it and interpret it in context. Pause the video, try to answer it on your own, and unpause when you are done. Okay, let's see that answer. The intercept is approximately 72.95. Now, first off, where do we get that? Well, we need to look at constant. All right, this is going to give us some information about the intercept. All right, and under coefficient, we see 72.95. Okay, and we have some information over here that for our intents and purposes doesn't really matter in this problem. We're looking for this value right here. Okay, 72.95. This means the average time to finish checking out if there aren't any other customers is 72.95 seconds. Now, why is that? Well, this is the intercept, the y-intercept specifically, for our regression line. And the y for a y-intercept, the x value is 0, and the input is going to relate to the customers waiting in line. So if we have 0 customers in line, then that means the time in seconds that we're going to have to wait, we predict, is 72.95. Now let's look at part B. Identify and interpret in context the coefficient of determination r squared. And by the way, our textbook likes to call this the variation accounted for. Okay? So we're going to identify and interpret in context the coefficient of determination or variation accounted for r squared. Pause the video, try this one on your own, unpause when you want to check your answer. All right, I assume we're ready to continue. The coefficient of determination or variation accounted for is r squared is equal to 73.33%. Now, where did we get that? Well, it's this guy right here, 73.33%, the r-sq, that's the r squared value, coefficient of determination. R squared adjusted, just ignore it. You never need to use it for our intents and purposes. So what does it mean? This means 73.33% of the variation of time to check out is accounted for, hence variation accounted for, or explained by, that's another way of saying it, the number of customers in line. Now let's look at part C. One of the data points was determined to be an outlier. Circle the point on the scatter plot and explain why that point is considered an outlier. Okay, see if you can find that outlier and explain why the point is an outlier. Pause the video, unpause when you are done. Okay, let's see if we can get this one. Well, the point that you probably found is this one right here. So you'd want to circle that point right there, okay, as I am circling it with my mouse. The outlier is the point for which x equals 3 and y is just above 0. This point is an outlier because the y value, that is the time it takes to check out, is much lower than what the regression line predicts if 3 customers were in line. That is what makes it an outlier. Here's the next problem. An environmental science teacher at a high school with a large population of students wanted to estimate the proportion of students at the school who regularly recycle plastic bottles. The teacher selected a random sample of students at the school to survey. Each selected student went into the teacher's office, one at a time, and was asked to respond yes or no to the following question. Do you regularly recycle plastic bottles? Based on the responses, a 95% confidence interval for the proportion of all students at the school who would respond yes to the question was calculated as that. Question A. How many students were in the sample selected by the environmental science teacher? This is a pretty interesting question to start out with, but it's one that we can absolutely answer if we know the right formula. We're going to need to look at this confidence interval, of course, and we're also going to need to note that this is a 95% confidence interval for a proportion. See if you can put the pieces together and find the sample size that got you a 95% confidence interval that looks like this. Pause the video and then unpause the video when you think you have a solution. All right, let's look at the answer. So first we need to note that p hat is going to be the mean of the lower and upper extremities of my confidence interval, which is going to be 0.7. That means that the margin of error is 0.816, that's the upper extremity of my confidence interval, minus 0.7 is equal to 0.116, all right? So that is going to be my margin of error, okay? Now, there are other ways of doing this, but I taught you a formula that has n explicit on one side of the equation. N equals p hat q hat times the square of z star over the margin of error, right? Now it's just plug and chug. We're going to use that to find the sample size. P hat, as we found, is 0.7. Plug it in. Q hat, or 1 minus P hat, would then be 0.3. Where'd the 1.96 come from? That is the Z star value for a 95% confidence interval. And we need a Z star value because we're finding a confidence interval for a proportion. So we use the Z model. 0.116 is the margin of error that we found before. Plug and chug, we get 59.9. And of course, you can't sample that many people. As Dr. Seuss says, a person's a person no matter how small. So that 0.9 we'd round up to the nearest whole number, which would get us to 60. That means that we must have sampled 60 people in our study. Now let's move on to part B. Given the method used by the environmental science teacher to collect the responses, explain how bias might have been introduced and describe how the bias might affect the point estimate of the proportion of all students at the high school who would respond yes to the question. Consider how the technique the environmental science teacher used to collect responses could introduce bias. Pause the video, give it a thought, and unpause to check your answer. All right, I'll assume we're ready to continue. There may be bias because students are giving their responses to an environmental science teacher. They may say yes when they don't recycle because they assume the teacher cares about the environment. This might make the point estimate of the proportion of all students at the school who would respond yes higher than it should be. All right, let's look at part C and note that there are two parts to part C. The statistics teacher at the high school was concerned about the potential bias in the survey. To obtain a potentially less biased estimate of the proportion, the statistics teacher used an alternate method for collecting student responses. A random sample of 300 students was selected, and each student was given the following instructions on how to respond to the question. In private, flip a fair coin. If heads, you must respond no, regardless of whether you regularly recycle. If tails, please truthfully respond yes or no. So here's the question. What is the expected number of students from the sample of 300 who would be required to respond no because the coin flip resulted in heads? Don't overthink this one. The expected number of students is 50% odds of heads times 300 total students equals 150. Not bad, right? Number 2 gets a little more interesting. The results of the sample showed that 213 of the 300 selected students responded no. Based on the results of the sample, give a point estimate for the proportion of all students at the high school who would respond yes to the question. Think about how you would answer this, especially in light of your answer to problem 1. Give it a go. Check your answer when you think you have a good one. All right, let's look at part 2 of letter C. First, we need to note that 213 answers of no were given, but 150 were required, meaning that 213 minus 150 that we expect, that's from part 1, are going to be authentic. That means that 150 minus the 63 no's would be 87 authentic yeses. So the point estimate for the proportion of all high school students who respond yes is 87 out of 150. Okay, here comes problem number 3. Approximately 3.5% of all children born in a certain region are from multiple births, that is, twins, triplets, etc. Of the children born in the region who are from multiple births, 22% are left-handed. Of the children born in the region who are from single births, 11% are left-handed. Let's look at these 3 questions. Letter A. What is the probability that a randomly selected child born in the region is also left-handed? Take a moment, try this one on your own, and then unpause the video to check your answer. All right, I'll assume we're ready to continue. Here's A. We're going to let L denote left-handed, M denote multiple birth, and S denote a single birth. We're going to use this throughout the whole explanation for this problem. So for letter A, the probability of being left-handed is equal to the probability that you are in a multiple birth times the probability that you're left-handed given you're in a multiple birth, plus the probability of being in a single birth times the probability that you're left-handed given that you are in a single birth. Since the probabilities of being left-handed depend on whether you're in a multiple birth or a single birth, we need to find the probability in this way. We are considering the proportions of multiple and single births and the proportion of left-handed people born in each of these scenarios. If we were to do that, the proportion of multiple births is 3.5%, as the problem says. The probability of being left-handed given you're in a multiple birth is 22%. The probability of being in a single birth is the complement of being in a multiple birth, which would be 96.5%, and the probability of being left-handed in a single birth is 11%. Put it all together, you have 11.385%, or 0.11385. Now let's look at letter B. What is the probability that a randomly selected child born in the region is a child from a multiple birth, given that the child selected is left-handed? So we're going to be computing conditional probability for this one. Pause the video, try it on your own, and unpause the video when you are done. Okay, let's look at answer B. The probability of multiple birth given left-handed is equal to the probability of both divided by the probability of being left-handed. Okay, this is straight off of the formula sheet that you will have on the AP test. Okay, the probability of being both in a multiple birth and left-handed is 0.035 times 0.22. All right, 3.5% odds of being in a multiple birth, and of those, 22% are left-handed. Then we divide by the probability of being left-handed, which we found back in part A. That's 11.385%. If you were to do that division, you would get about 6.76%. Okay, let's look at letter C. A random sample of 20 children born in the region will be selected. What is the probability that the sample will have at least children who are left-handed? Here's a hint. That scenario describes a particular probability distribution. See if you can remember which probability distribution it is and try this one on your own. Unpause the video when you are done. All right, I'll assume we're ready to continue. Here comes part C. Now, I choose to do this one a little bit differently than College Board, though I will show their answer. Let X represent the number of children who are left-handed in a random sample of 20 children from the region. We're going to note that X fits a binomial model with n equals 20, and the probability of success is 11.385%. That we found in part A. Then the probability that X, meaning the number of children who are left-handed in a random sample of 20, is the probability that X is greater than or equal to 3 is equal to 1 minus the probability that X is less than or equal to 2. All right, so we've found that we can use the complement of the event here. All right, and the calculator has a neat feature to do the complement, this calculation right here. I'm going to do 1 minus binom CDF. Binom CDF computes the combined probability of X equals 0, X equals 1, X equals, and on and on and on until you hit your max, all right, which we say is the X value. Binom CDF has 3 arguments. We would say trials is 20, probability of success is 11.385%, and X value, where we're going to stop computing probabilities, is 2. So binom CDF calculates the probability of 0 children from the region, 1 child from the region, and then 2 children from the region, all separately being left-handed out of the 20 in total, right? So what are the odds of each of those 3 events? Okay, so if we do 1 minus that, we would find the probability X is greater than or equal to 3. There are 3 or more children in that region out of 20 who are left-handed. And that probability would turn out to be 0.402. Here's the answer from College Board. They did the same kind of process and the same kind of setup, except that they used the binomial probability model explicitly. So for the calculation for 0, they did 20 choose 0, odds of success to the 0, odds of failure, which is 1 minus the odds of success, to the 20th. And we have 20 choose 1, same deal, odds of success to the first power, odds of failure to the 19th power. And then we have 20 choose 2, and we have the odds of success squared, odds of failure to the 18th power, right? That's going to be 1 minus 0.598, which gives us the same answer as over here, all right? So we find the complement of the event. And by the way, this is a little bit sneaky. Just want to make sure you see this. College Board did distribute the negative sign to each of these binomial computations. All right, there you go. There are the first three problems.